There you go. All right. Welcome everybody to today's edition of the point distribution webinar. Thank you all for attending. Um, Couple of quick things. One is that we are intending to continue this webinar into the summer. So you can expect an email about that soon. We're of course looking for speakers. So if you have any suggestions or if you're interested in giving a talk, please do let us know. Um, Also, after the talk, there will of course be time for questions, and then after that, there will be time for tea socialization for anyone that wants to stay on. You're always encouraged to. Yeah, so those are just a few quick things. Now, today we have Xuemei Chen from the University of North Carolina, Wilmington, talking about frame design using projective energy.
Okay. Hi, everyone. So, um, thank you for the invitation and thank you for coming. Um, that so you can stop me anytime during the talk, or you can put in the chat. I can actually see everything, and because I have like two monitors, this is why if you look at me, I'm like kind of looking at at a weird angle. So anyway, so this is joint work with Doug and Ed at Vanderbilt University, and so the paper is already out. It's on archive, and I believe the organizers will have link to archive and everything, the talk and video afterwards, so you can read more about this work. And um, okay, right. So let me focus on frames first. And I know probably a really good, if not the overwhelming majority of the audience here know what is a frame. But I was also told to be make sure like this talk should be accessible to graduate students and then all that. So I might still go kind of slow and just see what happens. So um so a frame is kind of like a extension or generalization of a basis. So on the left, I have this orthogonal basis, and on the right, it's like an over complete set of vectors. So there's three vectors in R2. So that would be a frame. So that's just a visualization of a frame. And then here's just the official definition that we have a Hilbert space H, and then it needs to satisfy this inequality here that we have a lower upper bound A and B, so they're called the frame bounds. And my frame vectors are usually going to be little xi's, and altogether that would be my capital X. So that would be kind of the notation throughout this talk. And so if you have the bounds are equal, then it's called a tight frame. And so typically a tight frame is a pretty desired frame, and then you would have this nice, basically like a Parseval kind of identity to recover your vector from these coefficients, the inner products. So that would be like an official definition. But really think of a frame as like a over complete set of vectors, and so would span your original Hilbert space. Um, and so I was talking about that a tight frame is a desirable feature for frames, and then there's many others. So these magenta color, so it might be good if the norm of each frame vector are equal or more or less similar. And also sometimes it's good to have certain kind of symmetry within your frame vectors, and often we have seen that like a lot of nice ones do resemble certain kind of symmetry, whether it's in terms of geometry or certain group actions. And then it's also really nice if your frame vectors are like kind of apart from each other. So I'm going to call that well separated frames. And I will make that a little bit more specific in a second. But so pretty much these what I'm gonna call the good desirable properties of frames, and can do all sorts of good stuff here. So some applications over here and references, and also I somewhere I meant to include also reference, like, so I'll just hold here. I think this is a it's hard to see. This is also a good book by Shane Wagen about finite frames. So anyway, next. Oh wait, is there? Okay, there's no question yet. So, and then more notations. Okay, so this is gonna be the set of all unit norm frames. And D is going to be for the dimension, and capital N is going to be the number of points here. So pretty much this is a point configuration, point distribution kind of talk. The collection of endpoint configuration and things that make them unit norm, so they're on the sphere. And at this point, it can be either real vector space or complex vector space. Okay, and then so that's the notation. So once again, little d is for the dimension and capital N is for the number of points. And also it's nice to rewrite my set of points as like a matrix. So each point is going to be a column. So that's very conventional notation. And so then so here I listed several properties, but in this talk, I'm only going to be focused on 2 of them. It's really hard to get everything. So I'm going to be focused on finding a frame that's like tight-ish. And if it's exactly tight, that would be even better, but tight-ish. So this can be rewritten as this equation that X times its conjugate transpose is going to be the identity matrix in dimension D. And because it's unit norm, so we can compute the frame bound, so that it has to be N over D as well. And so number 2, property that I'm going to be focused on is the well separation. So I said that I will be a little bit more specific, and here it is. So this is a concept that's pretty common in like the commuting frame theory or compressed sensing. So I'm going to define coherence. It's basically like the worst angle possible, but since they're unit norms, so it didn't have to be divided by the 2 norms. And so yeah, you find the worst angle, and imagine if you had an orthogonal basis, so that's the best case in scenario, then you get coherence equals 0, because even the worst is give you 0 inner products. So coherence is the maximum of all pairwise inner products among your points. And so, okay, right. And it's pretty easy to realize that if we want to find the point configuration that will minimize the coherence, right, make it the best possible. So this is really pretty much like a best line packing problem, which has been so a very seminary work would be by Conway, Harding, and Sloan on packing lines, planes, basically Grassmannian spaces. And so you can say this is a best line packing problem, and pretty much just the definition of frame, all these properties naturally lend itself to just be on projective spaces, so which we will do today. And So you can call it a best line packing problem, or you can also say it's the best packing problem on the projective space. So either way, however you would like to say it. And so that's a little bit more details about well separation. So once again, we want to have these two properties, okay? And then so the first thing that came to mind with these two nice properties would be what we call an ETF, equiangular tight frame, because when you have that, then you have exactly tight, and then you also have that the pairwise angles, they're going to be constant. So hence equiangular. So and which will make the best separation. And so if you have ETF, you already have these two really nice properties, but it's hard to come by. And yeah, and oh yeah, so here's the book that I find myself to use frequently. But also, so I was saying that it's not easy at all to find ETF. There's many literature on that. And so I'll just point you to this one, which is supposedly like a living existing table of equiangular type frames. And then there's good references inside that paper. And so I think many of us know already that, for example, in the complex space, you have to have the number of vectors and being less than or equal to dimension squared. In the real space, you have to do b at most d times b plus 1 over 2, but that's just like the easiest constraints. And then there's other constraints. So they're hard problems basically. And then yeah, for the complex case, I believe that Casso gave a talk maybe several weeks ago here on, basically ETF in complex place, but specifically when the number of vectors is maximized, when you have n equals d squared. So that's also interest to the quantum information community. So anyway, so this is just like the first thing that often came to mind when we talk about these two nice properties. And so that's that. And then so let me talk about other works that kind of point to this direction. And so the first would be minimizing something often called the frame potential. So you would just right, you get a frame, or we can call it point configuration, maybe better here for this talk. And so you get a set of points, and then there are capital M points, and then you compute the pairwise inner product squared, and then you're gonna sum up. So you don't have to sum up the diagonals. You can for this here, but let's just get rid of it to be consistent throughout the talk. So no diagonal elements. And so you sum up all these pairwise inner products, and then you want to minimize among all endpoint configurations. So this is a well-known results by Benedetto and Ficus that right. So basically it says that it only gives you tight frames. It didn't say anything about well separation. And in fact, you can totally have a frame that's completely not well separated. So on the left and on the right, they're both tight frames, unit norm, but on the left, it's the worst separated possible because X1 are equal to X3 in the projective space, right? So it's like they're the same line. So there is no separation at all, or the worst separation here. Whereas on the right picture, so both of the two pictures are minimizers, and but on the left it's the worst separated. On the right is the best separated. Okay, so which means that if we minimize the frame potential, it doesn't give us well-separated frames necessarily. Okay, and so what about the more general p-frame potential? So here's some references on minimizing p-frame potential, and yeah, so just apologize upfront for I don't think my literature survey here is that complete, but I tried to basically pick out works that I think are fairly relevant and great. So anyway. There are many results I could also put on my slide, but in general, I think bigger p-value are going to promote better separation. And so yeah, so basically if p equals 2, it didn't work, but if you pick a higher p-value, it should work better. And actually, I haven't tried it numerically, just minimizing this p-frame potential and see how, like what kind of property it will have in terms of well separation and tight. So I actually totally should have done that in my work. Anyway, and then so this second result is also, it's pretty, it's in several different works, that if you have a big p, big enough p, and then when the equiangular type frame exists, that's going to be the minimizer as well. So it's not hard to prove. So I think that this result is in the work by Martin and Casso. Okay, so then, so this is gonna be our work here, that it will just be using a different energy that we minimize. And so the main result, I suppose, would be this slide here, that if we minimize a different kind of energy, it will produce nearly tight and well separated frames, meaning that, so I can sort of justify that it has low coherence. And then this kind of kernel, right? So this highlighted this numerator, denominator here. So why, I mean, I would just want to explain, it didn't look weird because this is really just the distance in the projective space. So in particular, if you want to do the embedding to the rank 1 matrices, then that would be the Frobenius norm. So that would be just one particular embed to the projective space. So it's really just the distance between the lines and to the s power. Okay, and that's why hence it's a kind of reads energy. And so anyway, just to summarize again, that the main result for our work is that we just try to minimize a different kind of energy, and then we can conclude, so there's theoretical and numerical support to support the claim that the minimizers are pretty good, pretty desirable frames. Okay, and so yeah, so right, so why this particular kind? So of course, when I do my setup or the theorem, I will make it a little bit more general. So we're going to be, so this kernel function f here would be in terms of that projective distance. And then in general, we just require f to be decreasing, and that's understandable, just to encourage the repels between the lines. And then we also would require f to be convex. And okay, so that's the general. And then here are several examples. So we can pick this kernel function to be t to the negative s power, or to 1 over log, and a log of 1 over, excuse me, or to this function, because if we use this particular kernel function, and then we will recover to the p-frame potential. However, very easy to prove that unfortunately in the third row it's not convex. So there's something to be said more about that. The first two, they're just really nice function, right? So if they are nicer than just decreasing and convex. It's like there's absolute monotone that so you can say they're really nice functions. So of course it's going to be decreasing and strictly convex. Okay, so that's just the general setup, and this is a reminder of that notation. This is just the collection of endpoint configurations on the sphere, so yeah, xi are on the sphere, and then I'm gonna just raise it to the rank 1 projections or rank 1 matrices. So that would be capital P, and then I'm going to claim that P is in this space here, the collection of all n point or n rank 1's configurations on the projective space. So right, and basically we already saw that, right? So the inside is just the distance between the rank 1's. There's nothing crazy about it. And so the first result is just on R2. Let's see. Okay, so yeah, so basically you have decreasing and convex function, and so which on the circle R2, and then we can claim that, so it's like a little result to get us started. We can claim that equally distributed points on the half circle, because I'm on the projective space, so I think it would be pretty easy. It would be pretty easy to I lost my chain. So it's on the projective space. So I'm just gonna draw half circle here. Okay, and then so it's equally distributed points on half circle here, so that they are gonna be the minimizers. And if F is strictly convex, and then so it's a good start, because this kind of configuration is, first of all, tight, and second of all, it is best separated among all possible configurations. So it is the best line packing. And what else? So it can be even more nicer things, like it's also, a spherical design. I think that depends on probably the number of points. So I forgot, but it's a spherical, maybe 2. Do I have? Yeah. So I think it's a spherical n-1 design if I have n points here. So it's like this configuration is very nice. It's exactly tight. It's best separated, and so it's good that when we do this kind of minimization, we do find it, right? So it's a good beginning. And next, so another good beginning would be going back to ETF, right? So hopefully we can at least find ETF by minimizing these frame energies or energies, if ETF exists, and that is the case. So so this is the second theorem here, but if you guys remember, right? So going back, so that theorem does not cover the P frame potential. So because it's not convex, like this function right here, it's not convex. So so then we do have a stronger theorem. So this here is it's called G, just a different function. But the point is that now it's actually in terms of your projective distance squared. And if it's in terms of that, then the G function that will produce your P frame potential, this actually now is strictly convex. And so this is a stronger theorem here, and we were able to just produce this stronger version as well. And so yeah, so this is stronger than the previous one. So that's why, so basically we can forget about the first half top of this slide, and this is like the actual theorem too. So here is just the, I think that's actually the full proof. So it's pretty pretty straightforward. That so I'm gonna start with the bottom half here, right? So this is the total summation is what I call E, the energy. So I start with the energy of that particular point configuration, and which is exactly this summation over here. And so it's being then using convexity, you can take the G out, and then so put the summation inside of G, and then you get this, right? So from this is why we were also trying to bound the quantity J. So this is basically the quantity J inside G. And so this is something really easy to bound. It basically comes down to the frame potential, and we know what's the bound of that. And so you go through these two inequalities, and then, you know, if you want to get the exactly equalities, you have to be equiangular type. So it's so basically it's pretty straightforward, just using convexity. I mean, of course, you also using decreasing. So okay, and then so more results here. Yeah, so I know I never defined what is a projective reads kernel, even one they already showed up. So let me do that here. So this is what we call a projective reads kernel. This function over here, and because it's just the very normal usual reads kernel. And but you know, we're on the projective space, so I think this name is fair. And the third theorem that we have here is about separation. Okay, so so first of all, like before I even present my theorems, right? So if you are a little bit familiar with a lot of the minimal energy results on Reed's kernel, then we can all imagine that I can really use a lot of results there to prove the theorems that I wanted. And because that my kernel here it is really the Reed's kernel, and now all I have is I have points, these points on the projective space, which is, you know, a compact manifold, right? So if in the Reed's energy literature, there are results about how the points are distributed on the compact manifold, and then I can just use that and put it convert them into my theorem. So a lot of them are results are just like that in the paper and in this talk. So over here, the dimension of the projective space, so it would be d minus 1 if we're in real space, and it would be twice of that if we're in complex space. So that is alpha. And so I'm going to pick this power S here to be bigger than alpha. And then I can get this result over here. So xn is going to be minimizer of this problem. And so remember, Kasi here is just the coherence, right? So Kasi is the maximum of the inner products, the pairwise inner products in absolute value. And it is bounded above. Okay, so let's just think what we want for a minute, right? So Kasi is coherence, and it would be good if it's small. Okay, so we want it to be small. We want Kasi to be oh, yeah, I cannot grab it. We want Kasi to be small. So the theorem says here is that, okay, yeah, maybe it can be bad, but here is the worst case in scenario. So so which has this bound that's less than 1, so we better have that. And so even though it's not a great bound, yeah, so first of all, the constant only depends on S and D, and the constant here is very specific. You can find in the paper. It's really specific, especially for the real vector space. And then the second of all, right? So this so depends on N, S, and D, all of these parameters, and also alpha, which depends on D. And so you have your constant, and then we can imagine that as N gets bigger and bigger, this is approaching 1, and that is completely unavoidable because you have really dense points on your sphere, so you have to be approaching 1, the best separation or the separation distance among the lines have to be approaching 1 no matter what. Or yeah, anyway, or coherence is what I'm doing here. And so pretty much that the proof of this theorem, like I mentioned earlier, is coming from the established results about Reed's energies. So, okay, so here it is that, so there's the work by Ed, Doug, and Whitehouse. And Tyler Whitehouse, yeah, that's right. And so they have this result about the separation. Yeah, so I should so delta here is the separation distance. So yeah, actually it is written here, right? So if you ignore the square, so the definition of delta here is just the distance between the point, but the smallest distance. And then we want to, so if it's written in terms of distance rather than in the product, so we would like to maximize this delta here, and so then you get best packing. So it does say that it can be, that's the worst case scenario, and then they compute constants and all that. So pretty much like this can just be somehow translated into this separation theorem. It's not hard at all, and just by this conversion here. So, and on the other hand, so yeah, I probably should have written here, but I just have to say verbally, sorry, that so even though this doesn't look like a great bound, but and so I think I haven't really found any literature, would provide an upper bound, like what's the worst case in scenario if for some particular kind of point configuration. And second of all, this is like basically optimal asymptotically. So even though it's bad, but this is, pretty much the best you can get asymptotically as N is growing. So at least there's that. And just so again, there any questions so far? Maybe I should have asked earlier too. Okay, so the next one would be the nearly tight theorem, right? So remember, I want two things. I want separation, I want tight or nearly tight. So we can sort of get that too. And so it's the same setup. We minimize the Reed's energy and the projective Reed's energy, and then we get a minimizer we call X, and then this minimizer does kind of conversion to the identity matrix, and it's it's because it's a pretty, again, established minimal energy results in like the continuous energy results that the counting measure, the discrete ones that can converge weak star to the uniform measure. And so there's a little bit other things to prove, like the what the uniform measure does here, and different other things. And but again, this is not a very hard theorem at all. So the disadvantage, no, I shouldn't say that, like the disappointing part of this theorem is that this limit is really not very strong at all, because that's actually not what we mean by tight. So next one here, right? So this is to criticize this theorem, like it's not good enough, because this is really what we should be having, that or hopefully we can have some kind of things like that, is right. So if this are equal, then you have exactly tight. And so some results like this, the Frobenius norm here is on the order of 1 over n to some positive power. That would be a really nice thing to achieve. So I tried pretty hard, but couldn't really do too much. So that definitely could be a future work, that some kind of like a quadrature approximation, right? So basically it's almost like you want to use discrete energy to approximate continuous energy. So there are work that I should have cited here. So there are work that's like QMC design certain things, and to kind of talk about the order of this difference, which can be written in terms of an integral, right? Integration and the discretization of the integration. And how that difference is progressing as n goes to infinity. So there's work along that line. And but maybe with the like we have really particular functions here. So my feeling is that it shouldn't be very hard to try something along this line in the future work, and especially the numerical experiments does turn out to be somewhat along that line. So which is what we're gonna see next. Okay, so yeah, I know this picture is kind of crazy, and yeah, I don't know. Okay, so here we go. That so first of all, I should really talk about how do I minimize my energy, because that is like a whole work of its own. So right, so when I minimize this energy over here, it was not sophisticated. I just used MATLAB, and MATLAB fmin function pretty much, but I do provide MATLAB with its gradient, so I would compute the gradient analytically and give that to MATLAB too. So and then and also feed MATLAB with an initial starter, okay, and then let do its thing. So this is how I did it. So yeah, so there's a lot of numerical issues could be definitely need to be addressed, and it's there are many for sure local minimizers. So most likely the results that's being shown in these pictures, they are local minimizers. And so usually I would try different initializations and try to pick lower ones. Anyways, so here the different color is corresponding to different values of S. And so yeah, S equals 0 would be the log case, and S equals -2. Yeah, so I should right, so this is pretty straightforward. So if you let S equals -2, then you will recover the frame potential exactly. And then, I mean, if S is negative, you will be maximizing this energy too. So it's not in the paper, but only in numerical experiments, we tried -S and maximizing that to see how it goes. So yeah, so if S is -1, which I tried, and this should be obviously should be a maximizing problem. Okay, so try all these different values of S, and so there's no doubt that the frame potential, which corresponds to S equals -2, gives the tightest frame, and that is, you know, it's proven by definition. Well, not by definition, sorry, but pretty much. And then you have other values of S. So yes, smaller values of S is better. Okay, and so that's about tightness. And then in the paper, so I'm not showing every result, but I did try to do some kind of fitting, and so like I said, if you do some kind of curve fitting, it does seem to have this trend for smallish values of S. And then this picture here is about coherence, right? So coherence can be 1 is the worst you can get, that's bad. And so the green color also corresponds to, now I see, yeah, these green little ones, yeah, they're like, anyway. Okay, so so they're big-ish, that's not good. So this kind of go along together with which slides, this over here, right? So if you try to minimize the frame potential, you often get ones that's really poorly separated. So so that's just going to be true. And okay, so yeah, some are exactly equal to 1. So you can usually you find really poor separated ones if you do the frame potential, but for many others, so if you have basically here for separation, big-ish values of S is better. So that's kind of like unfortunate, because we want 2 different properties, but then, you know, they have different trend for value of S. And then see, I make this bigger. So so the Sloan bound, so that's like this light blue color. This is the like Sloan has some kind of database for best line packing, or you know, in terms of even many other subspaces, different dimensions, whatever. So if we just focus on line packing, then you can grab, if so this is dimension equals 6, and then go up to 40 points here. So the light blue is basically kind of like the best possible that coherence that they have found. And so this should be yeah, like pretty much the lower bound here, which, you know, definitely shows up in the experiment. And then the other thing that we need to see from this picture is just yeah, bigger-ish S values gives you a little bit better results, just better separation, smaller coherence. Okay, and then so it won't go down. Okay, so so this actually provides a somewhat idea that to generate well separated and exactly tight frame, at least numerically, and then so that's something nice to see, you know, if you so okay, so we're going to start with a random frame. And by the way, yeah, so I didn't show in this talk, but random frame definitely behave bad in you know, whether it's tight or separation so way worse than any of the minimizers. So that should also be something we check in the first place. Like at least we should do better than random frames. So anyway, so we start with a random frame, and so you use that as the initial configuration, and then you do your minimization, and then for big-ish values of S. So then this minimizer, which we call Y, is gonna be most likely well separated and nearly tight. Okay, so we will have that, and then but you feed this Y as the initial configuration into the frame potential. So now if that is your feeder, then the output of this minimization problem, first of all, it's going to be exactly tight, but it will still kind of keep the well separation property. And so another future work I think would be very interesting to do is to kind of more provide theoretical justification for it. And this is related to the Poisson problem that if you have like a nearly tight frame, uniform tight frame, and then there's always like a exactly tight frame nearby, and which is proven. And so another interesting future work. And then finally, this is just the picture goes along with this method. So now everything else is the same, but for S equals -2, basically we just feed it, not rather than random initializers, we feed it with like a good starter, like a starter that's already well separated, and so it will become also fairly good in terms of coherence. Let's see. Yeah, I think that's all my talk. And so thank you very much. And if you have any questions, let me know.
Yes, are there any questions for the speaker?
I do have some question. So thank you, Xuemei, for the talk. I like it very much.
Well, thank you.
And I was wondering about the value of S, because there is a couple of things that I wonder about. One is that your theoretical results, if I understand, is for S bigger than the dimension.
Yeah.
But all the numerical experiments were S smaller than the dimension. Was it
okay?
true?
Yeah. Yes, that's all true. Well, except for so I did have strict inequality. So
Yeah.
so yes. So that's a really good point. And so in the paper, there are results that we have S bigger than the dimension. Well, oh, actually, no, 6 would qualify because it's D-1.
Oh, okay.
Okay, so at least there's 1 here. But yeah, so it is pretty computationally heavy to do a lot of things, like especially with my pretty poor computational ability. And so so there's other numerical experiments we tried when we had D equals only 3, and then so we tried other values of S. So there's similar results, but yes, so I believe that we should also be able to have something with where is it? Yeah, for the separation, we should also be able to have results even with small values of S.
Well, that's a big question, open question in the case of the sphere, if I remember well.
Yeah, I think so. So, but yeah, it's a good point.
Okay, and the second question, maybe a bit more technical because it might go into how you prove the separation, but it's not that I know the proof well, but I do remember this is the Poppy-Seed-Bagel theorem, right? And usually you would ask S to be bigger than the dimension for the result that says separation for minimizers of risk energy. But if I understood well, What you do with the projective space, you first embed it into an affine space of dimension d squared, probably, right?
Yeah,
Like
the bigger dimension, yes.
right? So then in order to apply this Poppy-Bagger theorem, should you not be needing to have s bigger than d squared?
I think it's so right, so maybe I can go into this a little bit. So here yeah, so I put here like what we call upper alpha regular measure. So basically the measure of like a ball should be bounded above by the volume of a ball with radius or something like that. And so with this kind of definition, I only need to show that the manifold, that's not the whole set, not where it's embedded to, but the manifold, so is actually upper like d-1 regular. And
okay, yes, good, yes, of course. Then you don't care about the dimension of the ambient space, but you care of the dimension of the manifold, of course.
right.
Yes, perfect. And maybe a last question about your algorithm. So if you can show it again to us, please.
Yeah. Like this one, right?
Yes, this one. So I don't know if you explained or not why step 3. I mean, could step 3 destroy separation?
So yeah, so actually I think the answer is maybe it won't, and so we don't know. So that would be something to study further, but the numerical experiment suggests that it didn't. If the y, yeah, if you feed it with a good separation configuration, it seems like it won't do it. It won't destroy that.
Okay, because if I understand you well, if you start in a bad configuration, minimizing only step 3 can give not well separated, right? So
right, that's right.
Okay, so the hope is if you give it a good one, then it will converge to the good place.
Yeah, so there should be a lot of local minimizers nearby, and it should quickly fall into the nearby one, which still kind of kept the separation is continuous.
Okay, perfect. Thank you very much.
You're welcome.
Other questions?
Xuemei, so you feed this, you have this third step just to satisfy the frame condition.
The tightness, yes.
Yeah.
Yes, that's right, exactly.
But do you have any guarantees? Do you have any theoretical results towards what Carlos was saying? If like when you do not degrade separation, things like that?
Yeah, no, I don't. So that again, that I think that's interesting future work. So the only kind of like the really loose guidance I have would be the affirmative of the Poisson conjecture, which does say if you have if you have a nearly tight frame, which is what Y is, then then within certain distance, you can find exactly tight frame that close to it. So I should have put a reference, but if you like go to Google Scholar, do Poisson's problem, it might come up like so it was proven a while ago, and then later got their names, but they like a group of people made the proof a lot simpler, which is really nice, just a few pages online. So yeah, that's really nice work. But no, I don't have like a solid support.
Although there should be some cases where you probably don't end up moving your points a lot, right? So between step 2 and 3. So have you checked if it's often that you have the same output? So you get some, because it seems for some of these, like for example, you had this 22 points in dimension 6 case, which is likely what the configuration is, right? That's probably the end of coordinate axes. Well, let's say we don't talk projective space, but the the embedded space, right? So not projector, but the actual sphere. So then 22 points is like 44 in this space, and what that is a hemicube. So every other vertex of the unit cube plus the ends of coordinates, right?
Okay.
So you have the axes of coordinates pass through the centers of faces of that cube, and you have the okay. So how do I describe it? It's a cube with edges parallel to the axes, right? And plus the endpoints of axes that pass through the centers of faces. So that gives you 32 points for the vertices of this cube plus 12 for the endpoints of the axes. Okay, so that's 44, and that's probably why you're getting some kind of 22 nice configuration at 22. So I'm curious. So it probably is likely that at least in this one case, okay, so why I know about this particular configuration is conjectured to be best packing in dimension 6.
Yeah.
Right?
Yes.
Yeah. So you're probably getting like a fixed point. I mean, you minimize Reese, you get it, and it probably is a tight frame. I don't know if it's a tight frame. So actually, I don't know.
Yeah. Is it? So let's see. It should be it. This is 5, 6, 27. That's 27 is tight. 26.
Yeah, 22 also is, no?
Oh, 22, excuse me. Yeah, 22, it will be tight, yes.
Yeah, so you're probably recovering some kind of optimal packing configurations every now and then.
Yeah.
Right, yeah.
Yes, yeah. So I think there's more are pointed out in the paper. Maybe I should put in the talk too. Yeah, so we do highlight certain ones that we point like the very pretty established configurations.
Right. Okay, thank you.
Any other questions?
So then, for example, points which are just very well separated, they are not guaranteed to be good from the tightness point of view, right?
Right. Yeah. So it's in the paper that there I do kind of draw out how tight like the Sloan configuration are. Let's see. Yeah, right. So again, so that would be the best separated, and so yeah, they're not good at being tight.
Other questions?
I have a question. Maybe it's a stupid one, but in the first slide, you use also convexity property and you use it in the proof. Do you have convexity property because you use it in the proof also for some other reasons?
Yeah, so the convexity you mean in earlier? So like convexity was just when we had a general, where is it? So yeah, so it was only for theorem 1 and 2, which we definitely need convexity. It can be disproven otherwise. And so for the later one, like more like kind of the goal of the talk, when there's separation and nearly tight. So I'm actually only focusing on like this very particular kind of energy, which like I said, it is convex, but it's even better, much nicer than that.
Okay, so without convexity property, it could be proved that the results will be not halt, right?
Can you say it again?
Without convexity property, it could be proved that the results are not true, right?
Right, for the first two theorems, yeah.
Okay, thank you.
Could you maybe comment also on equation 5? So you mentioned there may be some QMC results that are similar to this. So could you maybe explain some more? Yeah.
Sure. So that is, like I said, something I tried pretty hard but couldn't get anywhere. And so let me see if I can find the paper. So the paper is, wait, can you still see my screen?
The slides, yes.
Yeah.
We can see your slides.
Okay.
The slides.
So can you see other PDF?
No.
Oh, okay.
Only the
So
slides.
I can reshare. Let me see if I can find the other paper. So I just have a lot of papers open. Yeah. Is it okay if I just share that paper?
Sure.
Okay, so stop share and share. Let's see. Okay, so yeah, so this is one work that I felt maybe could go somewhere, right? So this is kind of like in order in terms of the number of points, and then we can, like, whatever I want, it can be written in terms of like an actual integral, the difference between the continuous and the discretized version, and so that's why it's really kind of like a quadrature problem. And but what they have here is like really strong assumption. They have that the function is in like a Sobolev space, but I think all I want is the function just needs to be like a polynomial up to degree 2, because that would give me the type all these x, y, x, I, y, x, I, x, j kind of terms. And so I think so they are only able to prove something not very strong, because that their function is already pretty nice, but I think the function I need is even nicer, just polynomials up to degree 2. So I was hoping that if I have that nice kind of function, I can prove something in terms of the, like, discrepancy quadrature things, but but yes, just more work to do. So does that give a better idea?
Yes, thank you.
Okay.
Any other questions? All right, in that case, I'm going to stop the recording.